So today I have a meeting, so you get a video. Hopefully it's short and then you have time to work on some stuff. So we started talking about last time how log functions and exponential functions are inverses of each other. Um, to solve an exponential function that cannot be solved by getting a common base, you would use a logarithmic function. Really quick, let's talk about log functions. So if we have log base 2 of 1, log base 2 of 2, log base 2 of 4, log base 2 of 8, and so on, we can actually get legit answers for those. And we have a couple ways that we can do that. Now, if we're looking at what's actually happening here, if we have log base 2 of 1, that's the same thing as log base 2 of 2 to the 0 power. If we have log base 2 of 2, that's the same thing as log base 2 to the first power, and so on. And so what you're noticing is that whatever the base of the log is, if the number on the inside of the log is the exact same, and then we have an exponent there, then we can just make the answer the exponent. So you can kind of just look at this chart and see what's going on. Same thing over here with log base 3, or we could do it for log base anything, like log base 9 of 81 is going to be 2, because log base 9 of 81 is the same thing as log base 9 of 9 squared. So if we're looking at a problem like this, we have log base 4 of 8. That's going to be 3/2. And the reason we know that is because 8 is 4 to the 3/2. So if we can somehow convert this number to be in terms of the base of the log, then we can figure out an exact answer for some logarithm. And that's because logs are inverses of exponential functions. So if I have log base, if I have log base 3 of 7, I can't do that because 7 cannot be written as 3 to some power in a nice way. But I can say, even without a calculator, that this is going to be somewhere between 1 and 2, because I know that log base 3 of 3 is 1, and log base 3 of 9 is 2. And so I know that log base 3 of 7 would be somewhere in between 1 and 2, and it's probably closer to 2 than it is to 1, by a little bit. So if we're taking a look at why this might be the case, let's just really quickly, once again, go over how to rewrite functions. So if I have log base 4 of 64 equals 3, if I'm given that, I can rewrite this in exponential form, because I can take 4 to the power of both sides, and 4 to the log base 4. That essentially kind of cancels out, because they're inverses of each other. And so I end up with 4 to the 3rd power equals 64. But I also could have done this by recognizing that 64 is really 4 to the third. And so then what I can see is I can see log base 4 of 4 to the third is going to be 3, because log base 4 of 4, that's always going to be 1. Notice that if I have log base 2 of 2, that's 1. Log base 3 of 3, that's 1. So that's something that we might want to notice as we get going here. So that then leads us to another property of logs. If I go to this screen again, notice that log base 2 of 2 is 1, and then the answer was always whatever the exponent of this was in this case. So if I have a log function, like for example, log base 3 of 27 to the x power, because this exponent always ended up being the answer, and then this was 1, that works in other ways too. So this is an easy way to see it. If I look at this problem, not only could I rewrite 16 as 2 to the 4th, I could rewrite 16 as 4 squared. So let's say I have log base 2 of 4 squared. Log base 2 of 4, I already know is 2. Okay. But let's say that I take this exponent and rewrite it as a multiplier in front. So now I have 2 times log base 2 of 4. And I know that log base 2 of 4 is 2. So 2 times 2 is 4. Well, that was exactly what we said the answer was. So a property of logs is, if I have an exponent on this big number here, I can write it as a multiplier in front of the problem. So I could write this as x times log base 3 of 27. And since I know that log base 3 of 27 is 3, I can rewrite this as 3x. So this makes logs a really nice way to solve problems where we have variables in the exponent. That then leads us into solving some problems. Now, these are problems that we did on Friday. So if I have 3 to the x plus 4, I can rewrite 27 as 3 cubed. So then, since the bases are the same, I can say that x plus 4 equals 3, because I can just make the exponents equal to each other, and x equals -1. Likewise, over here, I can say 3 squared to the x plus 4 equals 3 cubed. And this is kind of annoying to write this way. One of the hand tools is not available, so I'm basically just trying to use a mouse to write. So then I can set the bases to be the same, or I'm sorry, the exponents to be the same. So 2x plus 8 equals 3. So in this case, x equals -5 halves. Those problems aren't that hard. But if I get to problems like this, I can't do what I did in previous examples, because 3 and 7 aren't the same base, and I can't get them to be the same base. So what I would do is I would take a log of both sides, and it's log base 3 of both sides is probably what I'm going to want to take. So log base 3 of 3, the x plus 4, equals log base 3 7. Now if I have log base 3 of 3 to the x plus 4, I can rewrite that as x plus 4 times log base 3 of 3 equals log base 3 of 7. Notice that log base 3 of 3 is 1, so I can say that x plus 4 equals log base 3 of 7. Then I can subtract 4 from both sides. So my answer is x equals log base 3 of 7. This is super hard to do. Minus 4. So log base 3 of 7 minus 4 is our answer. You can get an approximate on the calculator. So log base 3 of 7 minus 4 actually has a calculation. So log base 3 of 7 minus 4 is approximately negative 2.229. So that would be how you do that. Finally, let's do one last problem. So if I have log base, or I'm sorry, 3 to the x plus 4 equals 7 to the 2x minus 5, this problem is a little bit harder. What I'm going to do is I'm going to take a log of both sides. So if I take log of both sides, I have log base 3 of 3 to the x plus 4 equals log base 3 of 7 to the 2x minus 5. We know from the previous problem that the left side of this ends up being x plus 4. You know that the left side of this, I can simplify that to be x plus 4. And then the right side of this is log base 3, 7 to the 2x minus 5. This ends up being a lot harder problem than the previous problem. So I can move the 2x minus 5 to the front, and then that gets rid of the exponent. So now I have log base 3 of 7 equals, I'm sorry, log base 3 of 7 times 2x minus 5 equals x plus 4. So what I'm going to do then is I'm going to use the distributive property because I have to get all the x's on one side and all of the things that kind of look like numbers on the other side. So that's what happens to the right side there. Now I'm going to get all the x's on one side and all the numbers on the other side. Now I will factor out an x. Now all I have to do is divide both sides by 1 minus 2 log base 3 of 7. So if I divide both sides by 1 minus log base 2, or 2 log base 3 of 7, I now have my answer. So x equals negative 4 minus 5 log base 3 of 7 divided by 1 minus 2 log base 3 of 7. Some of you might be wondering whether you could have taken a log base 7 of both sides. You could have. Your answer would be the same, but it would look totally different. So your answer, if you typed it in the calculator, would look identical to this in terms of a decimal answer, but it would look totally different because everything would be in terms of log base 7s. And I get approximately 5.057.